talk?
Yeah, I don't know what about.
In what context?
I don't know, we're just talking. Told me that because I have to be there.
Uh-huh. All right. So today we are into my chapter 8, which I would assume is also Gamelin's chapter 8, as I wrote these notes to parallel Gamelin. And so Gamelin's a good book. I think the main problem for me with Gamelin going forward at this point is I've assigned most of the homework in it. So I kind of need to I need to make up some new problems, But anyway, so today we're talking about the logarithmic integral. And its applications, namely the argument principle and the Rouche's theorem. So let me get right into it here. So definition: if F analytic on domain D and gamma curve in D such that f of z is not equal to 0 on gamma, all right? Then 1 over 2 pi I integral along gamma of f prime of z over f of z dz is equal to 1 over 2 pi I integral along gamma of the differential of the log of f of z. Right. This is the quote-unquote logarithmic integral of f of z along gamma. So log integral of f along gamma is this. All right, great. So essentially the logarithmic integral measures the change of the logarithm along the curve. All right. Now the first thing here, this is just a differential identity, right? In the definition, you see why this is a reasonable thing to write? Does that make sense to you guys? What happens if I take the differential of the log? Remember how the derivative of the log is? It's 1 over f of z, right? But then chain rule says times d dz of f of z, which of course is f prime of z over f of z, right? So, and the differential I lost my dz, sorry about that. Well, let me write it this way. This dz, there we go. Now it's legit. And then you multiply dz to the other side, and you got it. Okay. So anyway, it's the differential. So let's see here. Warm up calculation. Example 1. Let's let f of z equals z minus z naught to the power n. All right, for n an integer, some integer, all right? And then let's look at the unit circle gamma parameterized by z equals to z naught plus r e to the I theta, right? And we'll say for 0 less than or equal to theta less than or equal to 2 pi k. Here k is an integer. So what this is depending on what k is, if k is just 1, it's going around the circle once, right? If k is 0, it's not even going around the circle. k is equal to 2, you're going twice around the circle. And if k is negative, it doesn't really make sense as I've written it, does it? So, anyway. So I probably should say for k in natural numbers, I think, as I've formulated this. All right, anyway. So what's the logarithmic integral of this function? 1 over 2 pi I integral of f prime of z over f of z, which is what? 1 over 2 pi I integral from 0 to 2 pi k. Why is it so hot in here? 2 pi k. Here f prime is what? N times z minus z naught to the n minus 1 divided by what? Z minus z naught to the n, right? I guess let me drop the 2 pi k here. I'm actually just doing the complex integral here at the moment, right? So what do we got? We've got 1 over 2 pi I, integral from 0 to 2 pi k, and that just gives us 1 over z minus z naught to the 1 over z minus z naught, right? So that's what? dz is, what is it? It's I r e to the I theta d theta, right? And then this just simply, I've got an n, right? There's an n. Don't forget the n. And see the n over n minus, the n minus 1 upstairs and the n downstairs just leaves me 1 z minus z naught, which leaves me a r e to the I theta. So what happens? Yeah, it just leaves us with id, but the i's cancel, right? So we get what? We get n over 2 pi, right? Integral of d theta, which just gives me what?
The balance just subtracted.
Yeah, so I get the 2 pi's then cancel, and I get n times k.
Where's your I popping out? Oh, I see now.
Yeah, from the dz. All right. So let me try to explain what's going on here. So the k in this case is so k is characteristic of our parameterization of the curve, right? So this k here is called the winding number. It's how many times we've wound the curve around the unit circle, right, in the counterclockwise fashion, right? And n, well, n is the, what is n? Now, I'm assuming k, just because of my parameterization, k has to be positive, right? But you could just as well put a minus. See what you could do here? You could put like a minus theta instead of theta, and then you'd be clockwise parameterizing it, and you could go through the same calculation. You'd still get, I believe you'd get minus nk if it was clockwise, k-fold wound. So you can actually think of k being positive as being a counterclockwise wind, whereas k is negative is a clockwise winding of the unit circle here. But the larger point here is that n could be positive or negative, right?
Just has to be an
Right, but what would the difference be if n is positive? What is? So if n is greater than 0, then f of z has blank of order blank at z naught.
singularity of order 1.
Is it a singularity? If n is positive, what do we got?
A 0?
Yeah, it's just a 0. So it would be a 0 of order.
It's a pole, right?
Yeah. On the other hand, if n is less than 0, it's a pole.
Yeah.
It's a pole of order n, right? So it has 0, right, of order n at z naught. So this logarithmic integral is doing what? It's counting something about the zeros or the singularities within the curve. All right, so that's essentially the argument principle. Let me write it down as a theorem. Theorem. This is argument principle 1. It says, let D be a bounded domain with piecewise smooth boundary, boundary D, and let F be meromorphic. What did meromorphic mean?
Meromorphic, I think it was holomorphic with is it the one where it's holomorphic and analytic? Because we said these are two different things.
So meromorphic means that it's holomorphic, except at a collection of isolated singular points, each of which has a pole of finite order. So it's basically, it's analytic everywhere except for some collection of isolated singularities, each of which is a pole, right? No essential singularities allowed. Yeah. So we're assuming that we've got a meromorphic function on this domain with piecewise smooth boundary, and the function's non-zero on the boundary. All right, then the logarithmic integral, all right, f prime of z over f of z dz, what is it equal to? It's equal to the number of zeros minus the number of singular points, number of poles rather, in D, counting multiplicities. Number of zeros, number of poles inside the boundary. Again, counting, counting multiplicity too. Like we had here, if I had in my example 1, if I had a 0 of order 3, I would have picked up a 3. And so we're also going to, and also unlike example 1, like in here, the boundary of D, we don't do some weird thing like winding around it 5 times, right? We just go around it once. That's our standard definition for the boundary of a domain, right? So the winding number does not come into play in this theorem either, all right? Think of k equals to 1 in my first example. So, if z naught is 0 or pole of order n, then f of z, it can be written as z minus well, let me z minus z naught to the n times g of z. I guess I should say 0 of order n or pole of order minus n, right? If I want to let I want the formula to be good for either case, yeah? I guess in my notes I just have 2 separate proofs. Maybe I should do that. I was reading Gamelin. I think Gamelin just does both at once. If you think about it, if n is positive, that's a 0 of order n, right? If the n is negative, then it's a pole of order minus n. But it's really the same formula for both. And here, g of z is holomorphic at z naught with g of z naught not equal to 0. So I'm going to be lazy and follow Gamelin here for class. What happens if we differentiate? What happens if we look at f over f prime? Rather, f prime over f.
Differentiating by z.
Yeah.
So you get r equal to theta.
Oh, no. This right here. So we get n z minus z naught to the n minus 1 g of z, right? Plus, yeah, z minus z naught to the n g prime of z. And we also know that g prime of z naught is not equal to 0, right?
Yeah.
Because if g prime of z naught was 0, then we wouldn't say it was a 0 of order n, because if g prime of z naught was 0, that would mean there's a z minus z naught factor in the analytic expansion about z naught of g of z, which is what we're not wanting, right? So, because we want it to be a 0 of order n, which means not just that g of z naught is not equal to 0, but,
And then you put it,
well, anyway.
so f,
I guess I'm not sure I know that. I feel like something's wrong with what I'm saying. Anyway, yeah?
then write f on the bottom and take a factor of z minus z naught to the n minus 1 of everything. So you get n z minus z naught n minus 1 out front.
So you said we got a,
Z minus z naught n minus 1 out front.
so we just get an n, a big N over z minus z naught.
Yeah, but you still got your g prime.
Yep, plus g prime of z over g of z. I guess g prime of, I'm not actually sure about this. I was saying that, but think about it some more. I feel like I can't say that. I shouldn't say that. I'm already assuming that g of z naught is not 0. So that does the job, I think. Oh, thank you. Sorry I'm behind my grading, by the way.
Okay, that's it. Okay, I got you, yeah.
So what happens when we integrate?
With respect to z.
So let me kind of draw a picture here. If you think about D, right? Piecewise smooth boundary, right? So you could have some breaks or whatever. This could be D, the boundary D, like that. And the thing is, there are a finite number, there have to be a finite number of singularities, because if they were infinite, then they'd accumulate, so they wouldn't be isolated. So there's got to be if the region's finite, they have to be a finite number, okay? If you had an infinite number of singularities in a finite region, you'd have an accumulation point for the singularities, which would mean they're not isolated. But, so there's a finite number of them, okay? And that means that you can do that sort of butcher shop deal and like we did in the other argument the other day, right? And we're assuming that the function is analytic everywhere except for those, it's meromorphic, right? Which means then you could replace the boundary of D with some like little circles, right? That enclose each singular point, or these are either singular points or zeros, right? So you can put a little little counterclockwise circle around each one of these guys. And you can replace the integral around the boundary of D with the integral over the circles, right? And what is the integral over one of these circles? Say the circle centered at z naught,
Like 2 pi I, like the
Cauchy's theorem. Yeah, well, it's let me write it out here. It's the integral of n over z minus z naught, right?
Yeah.
Plus g prime of z over g of z. I guess I didn't need to write that. You're saying Cauchy's theorem. I should have done that. That would have been good. So the circle centered at z naught, a small radius, But just like you said, Cauchy's theorem, it says that's 2 pi I times n. Right? Because the residue, the calculation above in black shows that the residue of f prime over f is just n. That's the coefficient of the Laurent expansion of the reciprocal power. The residue is n, big N. And that's true. We can do this calculation at each one of these singularities, right? Or poles, each one of these zeros. And so you add them together, and that's exactly what the theorem says. See, because we divide by 2 pi I, so that 2 pi I cancels the 2 pi I out in the residue theorem, and you're just left with the argument principle. Yeah? And then, let's see here, argument principle 2 says that the integral along the boundary of D of the differential of the argument of f of z is equal to 2 pi times the number of zeros minus the number of infinities up to counting. So let me kind of explain that. The differential, so remember in the definition I've already sort of explained to you that the differential of the log of f of z, right, is what is it? It's, well, let me look. We know that that's equal to f prime of z over f of z dz, right? Given the condition on the boundary of D, right? Where, what are we assuming? F of z is not equal to 0, yeah? So that makes sense, this calculation. But we also know that when we integrate that divided by 2 pi I, we get from argument principle number 1 the number of zeros minus the number of poles counting multiplicity, right? But what is the logarithm? What is the log of f of z? It's the natural log of the modulus of f of z, right? Plus I times the argument of f of z. But the thing is, the reason that the logarithm is not exact, right? The reason that the logarithm is not exact on the entire punctured complex plane, why is that? It's because of the angle jump, right? That's what makes us have to put a branch cut for the logarithm. This part is the piece which is offensive for, this is the part which makes us not allowed to say that the differential of the logarithm, that the logarithm is the differential of something else, yeah? But actually, if you look at this piece actually is exact. In the sense that if you integrate the natural log of the modulus of f of z dz over the boundary of D, this will just be 0. Let's see if I have a well, I'm not saying it quite right. I've lost my way a little bit here. Let me back that up just a second here. It's not the log directly I'm integrating, is it? It's the differential of the log, right? So when you calculate the differential of the log, there's two pieces, yeah? There's the differential of the natural log of the modulus of f of z, right? Plus I times the differential of the arg of f of z. So this we cannot assume is what's the word? I mean, this can't be assumed to be exact. You can't assume that the integral of this around a closed loop is 0 because it's adding up the change in the angle for some function around a loop, right? So take the function to be 1. You know, look at well, not be 1. Let the function be like z, for example. What would happen if you calculate the differential of, you know, the angle for z going around the unit circle? Well, the change of z going around the unit circle is going to be 2 pi, right? So this does not integrate to 0 along a closed curve for general functions. Certainly doesn't for f of z equal to z. On the other hand, this one, yeah, this one, we were assuming that f of z is not equal to 0. So if we have, you know, if we go around that boundary, right, we can say that this piece integrates to 0 because we can just like parameterize the outside. Well, I mean, you had to break it up into pieces and do it for each piece, but for each piece you get the difference of the logarithm at the starting point and the terminal point and the starting point of the piece of the smooth piece of the boundary, and then you add those up and they cancel until you get back all the way where you started. And so you end up with, like, if I just think of the parameterization of the curve just being one thing, it's easier to think about. You know, if I think of the boundary of D being gamma, where it's going from, say, A to B, you know, so gamma of A is equal to gamma of B, and so this would be like log of f's value of f of B minus log of f's value of A. I can do that meaningfully here because this function is continuous where f of z is not 0. I cannot make it a continuous assignment of the argument in general, unless I'm confined to a slit complex plane where I know the slit is that branch cut where I'm not going across it, right? It's fussy. But that's good news because that's what argument principle 2 comes from, because you see, while the logarithmic integral is the integral of the differential of the log, the piece of the differential of the log, that's the natural log, dies out when we integrate around the closed loop. And all we're left with is I times the differential of the argument, right? Which then gives us argument principle number 2. So. Let's see if I can find you guys a good example, or at least an example. I'll follow the example in my notes. Hopefully I won't regret it. So, example 8.1. 0.5 on page 163. Here we have f of z equal to z cubed plus 1. All right. And I'll let gamma of t equal to z naught plus r e to the it for r greater than 0, 0 less than or equal to t less than or equal to 2 pi. So that's a circle of I'm going to set r equals to 2 and z naught equal to 0. I could have just said gamma of t is 2e to the rt. That would have been just as good. Thank you for wasting my time, my notes. Anyways, so I'm an idiot. So what is f of gamma of t then? F of gamma of t would be here 2e to the it cubed plus 1, right? So that would be 8e to the 3it plus 1. So I'm explicitly calculating f of gamma of t, right? So what does, I say, okay, so the points traced out by f of gamma of t cover a circle of centered at 1, right? So I'm feeding the circle of radius 2 centered at 0, right? And then under the map f, right? What pops out? A new circle, right? Radius what? Not to scale, but the center of this one is 1, and its radius is 8. Yes, we should know this. Yeah. Now, but let's see here. This one, so here we had 0 to 2 pi, right? How many? So this one was covered once, right? So winding number k was 1 for this one. How many times do I wind around this one, though?
Why would you want more times than this one?
Because I've got the 3it. So 3it, as t ranges from 0 to 2 pi, this ranges from 0 to 6 pi.
Okay, so you want 3 times.
Yeah, k is 3 here. The winding number is 3 for this one.
Okay, is that because, how they're taking it is, that's the length of it?
That's because because f of gamma of t is this formula,
Yeah.
and so that is going from 0 to 6 pi. That's why it's 3. Why? What are you asking me?
I was thinking about geometrically, that's how many times you're winding around the original
Yeah.
to get the full thing.
Well, it's how many times you're winding around this circle to describe. This parameterization describes winding around this circle 1, 2, 3 times. All right. Now, in the notes, I have a picture of I don't know what my picture is of. Maybe that's of what? Hey. Well, that's aggravating. I feel like I got halfway through writing this example and just stopped. I'm a dummy. All right, so let's try to apply the argument principle to this thing, can we? Okay, so, all right, let's try. So what is I want to try to analyze argument principle number 2, right? What's the change in the argument of f of z if we look around the boundary of D? So this is literally a picture of f of gamma of t, right?
Yeah.
So if I just start at t equals to 0, right? And I go around here, I go around here once, twice, a third time, right? So the change in the argument, no. The change in the angle going around it, it's 6 pi. So from t to t equal to 6 pi, well, it's not t equals 6 pi, t equal to 2 pi gives me, 3, the 3it is what matters, right? So you're going around the circle 6 times, so that that change in the argument of f of gamma of t is equal to 6 pi. All right. So argument principle number 2 says that 6 pi, right, is equal to what? Integral. Did I ever move the camera? Or did I get lost in my thoughts and not do it? Sorry about that. So again, we have f of z is z cubed plus 1. We're looking at the curve, centered at 0 with radius 2, right? And we're studying the change of the angle of the image curve, f of gamma of t. The image curve here happens to also be a circle, which is easy to analyze. All right? Listen, the image curve for a more general like map could be really, really wacky if you just plot it directly. But anyway, the change in the argument of the image is 6 pi. So argument principle 2 says 6 pi is equal to, what is it? It's equal to 2 pi times the what? The number of zeros minus the number of singularities. This is for what? For the function f of z within the radius 2 circle.
Yeah.
So what is?
3 equals to.
But what about n? What is n infinity here?
How many zeros are in there? I think there's 1.
No. N infinity is the number of poles counting multiplicity. Are there any poles for this within the circle radius 2? Certainly not, right?
Yeah.
So this is straight up 0.
Yeah, so
Which,
zeros is 3.
so yeah, the number of zeros has to be equal to 3. This is a very simple example because we can find the zeros of this, right? What are the zeros of z to the z cubed plus 1? You've got, z minus 1 times z minus omega times z minus omega squared, where omega is the principal third root of unity. Right? And so, of course, where are those?
It's like on the 0 and then 2 out. It's kind of like a little peace sign.
Right, yeah, one's at minus 1.
Yeah.
One's at 1, rather.
1, and then it's like a peace sign thingy.
1 and here and here, right? The point is they're actually on the unit circle, right?
Yeah. So wouldn't there be more? Oh wait, no. Okay, we changed the radius. Never mind. Yeah, I was gonna think there's gonna be some on the circle, the 2 circle too. But if there were, that means we have them interiorly.
Right. See if I can find a peskier example for you guys. Well, that example is too pesky. Well, is it? All right, well, I will foolishly attempt a slightly peskier example. Actually, no, I won't. This will suffice. Now, next up, I will tell you what is Rouche's theorem. All right, so let D be a bounded domain with piecewise smooth boundary. All right, and let F be and F and H be analytic on D and its boundary, then if the modulus of h of z, all right, is less than the modulus of f of z, all right, for z in the boundary, then f of z and f of z plus h of z have the same number of zeros in D, counting multiplicities. This is Rouche's theorem. So here's the proof. By assumption, the modulus of h of z is less than the modulus of f of z. All right, and we cannot have a 0 on the boundary of D, right? F of z is not equal to 0 on the boundary of D. Does that make sense with the given data to you guys? Remember that the modulus of h of z can't be negative, right? So if you had that if you had f of z equal to 0, well, excuse me, if you had f of z equal to 0, it's impossible, right? See that? Look, this, if f of z is 0, notice it's not less than or equal to, right? See this? Not less than or equal to, less than. If f of z is equal to 0, h of z's got nowhere to go. Modulus of h of z's got nowhere to go. Okay, so f of z is not equal to 0 on the boundary, given that condition. And so also you can see that you have f of z plus h of z not equal to 0 on boundary D, right? If f of z plus h of z was 0, what would that mean? That would mean that f of z, that would mean that the modulus of f of z plus h of z, oh, excuse me, if f of z plus h of z is equal to 0, that means f of z is equal to minus h of z, which means that the modulus of f of z is equal to the modulus of h of z, which we have presupposed is not happening.
Yeah.
So that's also true. All right? Then f of z plus h of z is equal to f of z times, big parentheses, 1 plus h of z over f of z. Right, that's just algebra. Note where what? The modulus of h of z over f of z is what? It's less than 1, right? So, consequently, the real part of 1 plus h of z over f of z, right, has to be greater than 0. Okay, can you guys see that? Why is that true? Well, that's actually pretty obvious. If you look at the parentheses here, so what we're doing, we're taking 1 plus a complex number, right? See this? We're 1 plus a complex number whose modulus is smaller than 1, right? So the thing in square parentheses, in order for it to get negative, you would need to have the real part of this be less than minus 1. But that's impossible because the modulus of a quantity is the square root of the square of the real part plus the imaginary part squared. And we have that the modulus of this quantity is less than 1. So it's clear that this is true from that. And then what? So it says, thus, all the values of 1 plus h of z over f of z fall into the half plane, right? And that permits a single valued argument function throughout. Hence, any closed curve gives no gain in the argument function of 1 plus h over f. So this tells me then that the argument of f of z plus h of z is equal to the argument of f of z plus the argument of 1 plus h. See, this is probably, so this time, this is the point in the course where I feel guilty for not giving you the homework problem to prove that anytime you've got a product of two things, you can add the arguments, the multi-valued arguments, with the understanding that you can take a single branch of the argument. You can pick any branch of argument and this becomes an identity, possibly plus like a 2 pi or something. But anyway, the point is this formula right here gives us this. And then if we have, but the thing is, if we have a curve in the boundary, whatever the boundary D is, right, that closed curve, the image of this function along that closed curve, we can describe with a single argument function, which means that we can't ever like encircle the origin like we were doing in my previous example. We always come back to it. We can just use the, arg naught or something. And so this just gives us 0. Like the change in this piece gives us 0. And so the change in the argument of f of z plus h of z is the same as the change in the argument of just f of z, which then by argument principle number 2 says that in this case, the infinity is 0, right? So that then follows the number of zeros for f of z plus h of z is equal to the number of zeros for f of z. And that's Rouche's theorem. Now I have a picture to try to explain why this is true, but I will not attempt to do that picture right now. But what I will attempt to finish class with is a proof of the fundamental theorem of algebra. You're like, we're already out of time, right? Are we already out of time? 12:06. Okay, well I started at 12:09, so I've still got 3 minutes. I mean, wait a minute. That's not right. No time travel. So what is the fundamental theorem of algebra?
Things can be factored.
Things can be factored. Okay, so if we look at, let's say, f of z equals z to the n plus a to the n minus 1, z to the n minus 1 plus plus, a sub 1 z plus a0, right? Actually, I don't want to look at that as f of z. I'm going to look at that as f of z plus h of z, okay? So in this case, I'm going to let this be my f of z, and I'm going to let all of this be my h of z, right? So what's the modulus? Modulus of h of z is what? It's less than or equal to, the modulus of a sub n minus 1, modulus of z to the n minus 1, by triangle inequality, right? So that's a finite list of things, right? If the modulus of z is equal to r, right? Then let's see here. then this is less than or equal to what? Like, you know, an minus 1. Well, let me just say m. R to the n minus 1, yeah? Where m is like, you know, the maximum of the moduli of the coefficients or something like that, right? You can definitely make m big enough to make it that the biggest thing, right? But more than that, it shouldn't be too much of a stretch for you to see that surely we have that the modulus of h of z is less than the modulus of f of z for, if we look at a circle, right, with r sufficiently large, right? I mean, like, if r is big enough, then clearly the z to the n term is going to beat the modulus of the other piece, right? We can make r big enough such that the highest order term in the polynomial completely dominates everything else, right? Think of, if n is 3, this is quadratic, this is cubic. Put in a billion. A billion cubed is way, way bigger than a billion squared. And these numbers, and if these numbers are a billion, then you use a quadrillion or whatever. I mean, you can always play this game. The leading term wins in this sense. So then what? So if we use, how many zeros are there for f of z? But f of z equals z to the n has z naught equals to 0 n-fold repeated, right? What's that say then? By Rouche's theorem, f of z plus h of z also has n zeros, n-fold with, possibly repeated. But h of z plus f of z plus h of z is an arbitrary nth order polynomial. And that's the fundamental theorem of algebra. You see the gap in my argument. I haven't been careful about the estimate, but you could make this estimate careful without much more work. This to me is by far the easiest proof of the fundamental theorem of algebra that I know of, because it's built off the back of the largest collection of technical results in complex analysis, right? So anyway, we will look at more examples of Rouche's theorem next time, of course. So thanks, guys.